Quiero... Ya, ya no funciona. Dame los entonces.
Okay. Microphone. Is anyone taking notes? Is anyone taking notes?
I think it would be nice if, I mean, I don't know this, I think it would be nice if we do another session, so we have most of it then.
Yeah. Again, I think today is still less critical, but because most of you are studying similar things in Tali's course. Did you discuss differential entropy already? Not? Differential entropy? Okay, so good. So it's something new. Okay, so that's what we'll do today. Differential entropy. I mean, that's part of what we will do today. So far, when we discussed Shannon information, we discussed variables that take, maybe I'll just close the door. We'll discuss variables that take discrete values, right? And very often we're interested in variables that are continuous, and we want to understand how to extend or generalize the idea of Shannon entropy to such variables. So let's imagine that we have a certain continuous variable, x, and x has a probability distribution p of x, and it might look like this, just as an example. And so the integral of p of x dx from minus infinity to infinity is equal to 1 because it's a probability distribution. So this is now a probability density function. Now, how much information, how many bits would I need to provide to you in order to tell you what is the value of x? Why?
Because in continuous quantities there is infinite information left.
Okay, so you gave an answer. So you gave an answer. The answer is infinite. If you want to precisely, if I want to tell you precisely what is the value of x, I could represent it, say, as in a decimal system using all the digits after but I would need to tell you all the digits after the decimal point. So from.
But only if it's rational, and if it can be irrational, then.
Well, okay, so for an irrational, if you would want to get closer and closer to the value, you would need an infinite number of digits. If it's rational, actually you can maybe stop somewhere. So my point is it's infinite. Okay, I need an infinite amount of information in order to tell you exactly where the variable is. As long as I give you, say, a finite number of digits after the decimal point, you still don't know exactly what is the variable. Right?
I would just say
what?
nothing.
Okay. Seems I hope it's a small concern. Okay, so what can we do? One thing that we can do is think of a scenario in which we don't really care about the value of x up to infinite precision. And so let's imagine that we discretize x in bins. Let's see, at some point I will get tired of drawing them. Okay, I will at this point. Okay, so I draw bins of size, I divide the variable x into bins of size delta x. So this is now the rules of the game have changed. I'm not going to tell you what is x. I'm going to tell you in which one of these bins x falls. Okay? And of course, the smaller delta x, the more precise you will know after this what is x. But that's all we want to do. And now we have a discrete variable, right? So now we can apply Shannon's theorem and evaluate how much information I would need to, how many bits I would need to provide to you in order to tell you in which bin x has fallen. And what we will see is that the dependence on delta x once delta x becomes small, the dependence on delta x has a very well defined universal form, and therefore we can kind of characterize the continuous distribution using something that we will call the differential entropy. So to be more clear, let's just do it. So let me now define by age of x delta x the Shannon entropy associated with the variable that we just discussed, the discrete variable that tells you in which bin x has fallen. And so we know how to write it. But we will use the approximation already that if delta x is sufficiently small, then the probability to fall into a bin, into a specific bin, is just a product of the probability in that bin and delta x. So once delta x is small, probability to fall here would be p of x times delta x. So what does delta x need to be small compared to in order for this approximation to be true? Right. So it has to be. We are assuming what you can see here is that in order for this quantity to make any sense, we need to assume that this function is continuous. Okay. And then we need to. All we're doing our evaluation of this entropy will be correct, or very good approximation, when delta x is sufficiently small that this function doesn't change much within any interval of size delta x. So this is what we're assuming. Once we assume that, we can just write the entropy. So it's minus, we need to sum over the bins. So let's call the size, the bins xi. So let's imagine that this is xi, and we sum over all the bins. So sum over xi, the probability to fall into the bin xi, which is p of xi delta x. And I will do it, okay, let me write it with an S so that it will be in nits and not in bits. Ln p of xi delta x. And now this, just a second.
When you write the x, the argument of x is the continuous variable?
Wait, where?
The left step.
So this is what I really mean when I write x is the random variable x and its probability distribution. And now maybe it's nicer to do a semicolon here. What I want, this is a parameter. Delta x is a parameter of this quantity. Okay, so now as you remember, ln can be written as a product can be written as a sum of the lns. So we have here minus sum over xi, p of xi delta. So let me take this delta x outside, minus delta x, sum over xi, p of xi ln p of xi. And then we have another term which is minus delta x, sum over xi, p of xi, multiplied by a constant. The constant is just ln of delta x. So first of all, what is this? It's 1. It's just the sum of the probabilities to fall in any one of the bins. Another way to think about it we will mention in a moment. And what is that? What is this term? How can I write it differently? I'm thinking of a mathematical. So I have here, I go over the bins, I sum over a function of the position in the bin and multiply by delta x. Yeah, this is just how we define one of the ways to, the limit of this as delta x goes to 0 is a definition of the integral, right? I forgot the name. There are different definitions of the ways to define the limit. Does someone remember? Riemann. Yes. Okay, so I don't know if I can continue writing here, so you should tell me.
No.
No. Okay. And this, by the same token, is the integral of p of x, which is 1. This is another way to think about it. Okay. So what we have here is minus, actually delta, minus integral of p of x. And of course, this is approximately true, but approximately under the same actually assumptions that we used that to write from to assume from the start that the probability to fall into each one of the bins is simply p of x delta x. That's the same. The condition for that to be a good approximation is exactly the same condition for this to be an approximation of the integral. Because we are essentially, by writing this, we assume that the integral of the function within one of the bins is just an integral of a constant. So 1 minus p of x ln p of x dx from minus infinity to infinity. And then we have another term which is minus ln delta x. Maybe I can write it as plus ln 1 over delta x.
Why does it go from minus infinity?
Well, because in general I assume that x goes from minus infinity to infinity. And of course, if x is actually limited, then p of x will be 0 in those ranges in which x never takes values. Okay, so this is a very important outcome, because what you can see now is that as long as delta x is small, the only place where delta x matters is here. The dependence of delta x has always the same form. It's ln 1 over delta x. And then there's another term which does not depend on delta x, and this is what we call the differential entropy. So this is called, let's call that S of x, and this is called differential entropy. So just to summarize, what we got is that once we make a discretization, S of x delta x is equal to S of x plus ln 1 over delta x. And S of x, the differential entropy, is equal to minus the integral of p of x ln p of x dx, from minus infinity and infinity. So you see that the smaller we make delta x, the finer the bins, I would need to provide to you more bits of information to describe what is x, because if delta x is smaller, this is a larger number. The dependency is logarithmic, and it's all encapsulated. And actually, the dependence, once delta x is small, the dependence on the distribution of x is encapsulated in this quantity. And I want to emphasize, you often see this expression of differential entropy when people discuss entropy of continuous variables, and people sometimes tend to overlook what is the real interpretation. And that's the real interpretation, that if you would discretize a variable using uniform bins, meaning that the size of the bins is the same everywhere, then the amount of information that would need to be the number of bits it would need to provide to tell you in which bin you fall is this. And if the bins were not distributed uniformly, then this would not be the correct expression. Okay, so what can we say about this quantity, the differential entropy? So for one thing, I hope I remembered to say this, that the Shannon entropy that we discussed last lecture is always positive. Well, it has to be. It's a number of bits. This is a Shannon entropy, so this is always positive. But this can be positive or negative. You can see this by seeing that S of x is this minus this. And this can be a large negative number, or this can be a large positive number, so when you subtract it, you can get a negative number. So the differential entropy, in contrast to the Shannon entropy, can be negative. Well, actually, I don't have a list of properties, so I'll just point this out. And now I want to do some examples. So let's start with the most simple example that can be thought of, which is a variable x which is uniformly distributed within some interval. So p of x, let's imagine that x takes only values between x1 and x2, and the distribution is uniform within this interval, meaning that p of x is 0 here, it's 0 here, and here it has to be 1 over x2 minus x1 in order for p of x to be normalizable. So let's just see what is the differential entropy. So the differential entropy is minus the integral from minus infinity to infinity of p of x times 1 over x2 minus x1 times ln of 1 over x2 minus x1. Well, okay, so we will have the integral in these parts, but in these parts p of x is 0, so the integral will be 0. It's 0 times the ln, which is infinite, but the ln is this wins over, so we get 0 in these parts. So actually I will write the integral only from x1 to x2. And so I have an integral from x1 to x2, 1 over x2 minus x1, ln of 1 over x2 minus x1 dx. Now this is a constant, and the integral is from x1 on x2, so the integral multiplied by this just gives me 1. And what we remain with is ln of 1 over x2 minus x1 with the minus sign, so this is ln of x2 minus x1. Now, does this make sense? So to see whether this makes sense, we go back to this. If I would discretize now x in bins of size delta x, so if I discretize in bins of size delta x, this tells me that the number of bits that I would need to give you is s of x, which is ln x2 minus x1, or number of nits, right? Plus ln 1 over delta x, which is nothing but ln of x2 minus x1 divided by delta x. What is that?
The entropy of the discrete
uniform
distribution.
Yes, and this is just the number of bins. So this is ln of the number of bins. And we know that if we have a discrete variable that takes a certain number of discrete values and all of them appear with equal probability, the entropy, the Shannon entropy, is just the ln of the number of values. And if we would work in bits, it would be the log in base 2 of the number of possible values. Okay, so we see that this makes sense. Not surprising, but good to check. And let's do another slightly more interesting example. So this would be a Gaussian variable. So this would be example 1. And example 2 would be a Gaussian variable. So p of x is 1 over square root of 2 pi sigma square exponent of minus x minus mu squared divided by 2 sigma squared. This is the general form of a Gaussian variable with mean mu and standard deviation sigma. Okay, so we need to calculate the entropy, the differential entropy. So what do we need to do? We need to take the integral from minus infinity to infinity. I'll go a bit lower. Minus the integral from minus infinity to infinity, p of x. And now I will write the log of p of x. Okay? So p of x I want to leave for now written in this way. And now I have the ln of this. So the ln of this part will be minus the ln of square root of 2 pi sigma square. So we have here minus ln of square root of 2 pi sigma square. And the ln of this is minus x minus mu square divided by 2 sigma square dx. And now I claim that we don't need to do any work to really calculate these integrals. We know what they are. So what about this integral? Here we have something constant. Constant multiplied by p of x. The integral of p of x from minus infinity to infinity is 1. So we simply get this number, ln square root of 2 pi sigma square. Now, what is this? What is the integral of p of x, x minus mu square?
The non-femtile second moment.
It's the variance.
No, but you need to.
We took x, we subtract from it its mean, we square,
Yeah, you're right. You subtract from it.
and we take the average over the distribution p of x. So that's by definition the variance. I mean, once you know that mu is the mean of x, which it is, then this by definition, without the denominator, this would be the variance of x. So this is equal to, what is the variance of this variable? Sigma square. So when we take the integral p of x times s, we get sigma square, and it gets cancelled by the sigma square in the denominator. So we simply get a half. Okay, so if I want, I can write this sum also slightly differently. First of all, I can write this as half ln 2 pi sigma square plus half. And then if I want to put the half inside, I can also write this as half ln of 2 pi e sigma square, because the natural logarithm of e is 1. So that would give me this term. Okay. So again, the interpretation of this result is that if we have a Gaussian variable, normally distributed, and we discretize x in bins of size delta x, E times sigma square. So the interpretation is that if we discretize a variable delta x, then in the limit that delta x is very small, small compared to what? The only thing that could matter is the standard deviation. So when delta x is small compared to the standard deviation, that means that we're binning finely enough. In that case, the Shannon entropy associated with telling you in which bin the variable has fallen is given by what? It's given by this plus ln over delta x. So I could write all this together as ln half ln of 2 pi e sigma square divided by delta x square. Right? Because half ln of 1 over delta x square is ln of 1 over delta x. I just want to put some order. Okay. So this is the expression. And it's always good when you get some expressions to check that they, in terms of dimensions or units, they make sense. So if we imagine that x itself has some units, then here sigma has units of x squared, and this has units of x squared. So inside the LAN, we have something which is dimensionless. And so you see that what matters for, in this case, what matters for how much information I would need to provide you is the ratio between x2 minus x1 and delta x, right, which is the number of bins. And here what matters is the width of the Gaussian divided by delta x, right? Sigma divided by delta x determines the entropy of the Gaussian variable. Okay. Now the next example is, suppose that we have a variable x which is defined on some finite interval 0 to L, which means that we can think about it as a variable which is defined from minus infinity to infinity, but I already tell you that the probability to fall on a value less than 0 or larger than L is 0. And I want to ask the question, which P of x maximizes the differential entropy S of x? So the reason I'm doing it is that I want to also to introduce a mathematical way of thinking about things like this. You know how to maximize functions which are functions of some discrete set of variables. But here now we're doing something a little bit different. We want to maximize, so S of, let me first write S of x. We want to maximize minus the integral of P of x ln P of x dx, right? But, so what are our variables? What is the variable that we're varying when we're trying to maximize this? No, x is a variable. X is just the random variable, but what are we varying? P of x, right? We're varying a whole function. We have a whole function of x, and we're playing with the value of this function for each value of x. So we can think about it as if this function takes some value, can take a value for each value of x, and we're free to vary that function for every value of x, but that's a continuous set of variables. It's an infinite number of variables, which is the value of P of x for every value of x. So maximizing something like this is called functional, okay, if this was if our variables, if we think now of P of x as our variable, if this were a set of discrete variables, if x, say, was discretized and we had discrete set of variables, we know what we should do. We should take the derivative of this thing with respect to P of x. We need also to take a constraint. We remember what happened when we did it in the discrete case. We need to take the constraint that P of x is normalized. So we need to add some term which is a Lagrange multiplier, but we would take the derivative with respect to P of x and set it to 0. Here it's a derivative with respect to the value of the function at each element of x where x is continuous. So this is called a functional derivative.
Can you repeat that sentence? The derivative of what?
So we have here, okay, so maybe I will start by writing also the term with the Lagrange multiplier, okay, just so that we will be, we want to maximize this thing under a constraint, and the constraint is that integral of P of x from 0 to L is 1. So we will add a term with a Lagrange multiplier, which is the integral P of x dx minus 1 from 0 to L, and this is a Lagrange multiplier. Now, what is this thing? This is if we think of P of x as what we vary, This is a function of x, and all this is a function of the function, right? For every function p of x, this is a number. So something like this is called a functional. A functional is a function of a function. If you give me the function p of x, I tell you what is this thing. And so we want to find the function p of x that maximizes this number, right? And now what I'm telling you is that we can do it. If we don't think about it too much, it's very easy. You do it exactly in the same way that you would do it if this was a discrete value. You will think of p of x as a variable and take the derivative. And so I don't want him to go into justifying exactly what I'm doing. I'll just do it. And maybe with Neta, I will discuss it with more detail. Okay? So I will take the functional derivative of this thing with respect to p of x. And usually, when we do a functional derivative, we represent it like this. So let's call this L. And we want to take the derivative of L with respect to p of x and set it to 0. Okay, so the idea is that when we look, say, at this term, then I just take a derivative with the... Okay, so the proper way to do it now would be to remember that this is some specific x, and this is an integration variable. So we could have given it a different name, x prime. And now I want to take the derivative with respect to a particular p of x. Of course, we need to do it for all the p of x's. And so this involves only that, the integrand only when x prime is equal to x. So what I will write is the derivative of this expression with respect to p of x when x prime is x. So this would be minus... So this would be... It's okay? Okay. So this would be minus ln p of x. This is when I'm taking the derivative with respect to p of x here, and I get the ln. But I also need to take the derivative of the ln, so this would give me 1 over p of x multiplied by p of x, so this is minus 1. And then here, same thing, when I take the functional derivative of this with respect to p of x, I just get 1. So I get plus, but it's multiplied by lambda. So this I get lambda, and this should be 0. So this is very, very similar to what happened when we had a discrete set of values and we wanted to maximize the entropy. What you see is that from this expression is that p of x does not depend on x. Right? If this is true for all values of x, then p of x will be some constant. I don't need to even write what that constant is. It depends on lambda. But this constant needs to be set in order to, through varying lambda, such that we obey the constraint. And of course, that would just be 1 over L. So the differential entropy, the distribution that maximizes the differential entropy on an interval of length L is a uniform distribution. Just as much as the Shannon entropy that maximized the discrete distribution that maximized the Shannon entropy was a uniform distribution over the discrete values. So this makes sense.
Uniform distribution in a certain...
If I constrain the distribution to be take non-zero values within a certain interval, then within that interval, the option that will maximize the differential entropy will be a uniform distribution. And we know how to write the differential entropy in that case. We did it here. It would be simply the log of ln of L. So the maximal the maximal value of S would be just the ln of L. One last example that I want to mention is a similar question. So imagine that x is now defined on the whole range of minus infinity to infinity. And we are looking for a distribution that has some two constraints. One, we want that p of x, that x, the average of x would be mu. Okay? And second, we want the variance of x to be sigma square. So we can ask ourselves, given these two constraints, what is the distribution p of x that obeys these constraints and has a maximal differential entropy? So what is the p of x that obeys these constraints and maximizes the differential entropy? And I will just write down the answer. Does anybody know what's this? What, you discuss this with Tali or? What?
There are things on the board that imply.
Why?
Because you always like to use sigma squared in this Gaussian.
Ah, okay. No, but
It's not that clear.
no. Okay, so you can guess through the fact that I did an example of a Gaussian. That's the answer. It's not obvious at all, but it's true. So the answer is a Gaussian. The answer is a normal distribution. So this is 1 over square root of 2 pi sigma square exponent minus x minus mu squared divided by 2 sigma square. And I will leave that as an exercise. Maybe with I don't remember if Neta will do it or you will get it at home to do it at home.
Can you give an intuition for differential entropy?
Yes, one way to think about it, which is very useful, is to just imagine that instead of p of x being a continuous function, imagine that you would discretize x. And then p of x will just take a value in each value, and so replace every integral by the expression that we use as a limit, the Riemann delta x sum over all the bins of this thing multiplied by right? So replace the integral by the discrete approximation for the integral given in terms of the values of the function that you are integrating in all the bins. And so then imagine that the value of the function is constant in each one of the bins. Is uniform with each in one of them. And then you have a discrete set of variables, which is the value of the function in each. And then it's clear how to take a derivative with respect to each one of them. And that's what leads you in a more formal manner to the differential derivative, to the functional derivative. Okay? So it's like imagining that the value of the function in each bin is a variable that we can take and we take a derivative with respect to that. And so in here, for example, we have now in each bin it's a separate variable because it's the value of p of x prime in that bin. And so if I want to take the derivative with a p of x, it's just one bin that it depends on that, and in that bin we take the derivative of the integrand. Okay, let's see how we're doing on time. We have a few more minutes, so I will just introduce the next topic. And so after all this work, I want to do an example which is taken from the realm of neuroscience. So one of the most simple functions that a neuron can implement, a sensory neuron can implement, is some nonlinear input-output function. Now, many neurons, as you know, are spiking, so it's not clear what I mean by that, but there are some cases in sensory areas where we have neurons that receive a graded input, a voltage, and generate a graded output. Okay, so even in our retina, the photoreceptors are like that. They receive light, and actually the light is not graded input; it's photons, but they generate a graded output. And I will take an example, taking not from our retina, but from the fly retina. And there are some intermediate neurons in the fly retina that receive a graded input from a photoreceptor, and they generate a graded output. And so we can think about their function is just generating some nonlinearity.
What do you mean by graded?
Graded, that is continuous. It's not spikes. It's a volt.
The rate? The receptor potential.
Yes, yes. So so I'll think about the neuron as implementing an input-output function. And let's imagine that the input itself, which could be, say, the light intensity. So I don't remember now if this example actually. Yeah, so these are neurons that receive input from photoreceptors and generate an output. And so let's imagine that the output of a photoreceptor is simply proportional to the light intensity. And the light intensity itself has some distribution. And so our input, let's call the input, for now will be a bit more abstract. Input is X, but it could be, say, the light intensity. And what the neuron does is generates out of it, some output, which I will call R. And so this is the input, and this is the output. And let's imagine that R actually, the fact that I'm using R suggests that it is firing grade, so I need to check. I don't remember now for sure whether these cells, whether they generate spikes or they generate a continuous voltage. No, it's graded. So okay, so let's just call this the value R. So let's imagine that there is some limitation on the maximal output that this neuron can generate. And now I want to describe, first of all, the input-output function that the neuron implements. So maybe it looks like this. And this was measured, okay, a long time ago. Probably, okay, I will discuss a paper which is from 1981. And I think actually, I suppose that things like this were measured before that by probably Simon Laughlin, who did this work, measured this very carefully. And so he measured something like this, and we want to understand why is this the relationship between the input of the neuron and the output of the neuron. And this was one of the first works that applied to this kind of question of nonlinearity in a neuron, the tools of the efficient coding hypothesis. So,
how does
so you provide, so you shine light at different intensities. This is the input. This activates the photoreceptors, and then you measure the output of this neuron. You measure the output of this neuron.
What you have is like different intensities?
Yeah. This could be different intensities, and this is the output. And now Simon Laughlin hypothesized that this has to do with some form of efficient coding. So this is what we want to understand. If it has to do with efficient coding, then it has to do, the choice of this input-output relationship must have something to do with the distribution of the light intensities. So let's imagine that you measure also the distribution of the light intensities, and it might look like this. This is not 0, if this is intensity. Okay, this could be the log light intensity. Let's imagine that it might look something like this. And so we want to understand,
You mean natural stimuli?
yeah, and of course it's very important what are the stimuli. When I say that there's a distribution of light intensities, that depends on what is the distribution. So Simon Laughlin measured the distribution of light in natural settings. Light intensities in natural settings. So there are two different curves. This one is the input-output relationship of the neuron. And this, what I drew here, I actually didn't define it, so it's good that you asked. This is P of X. Okay? Two different scales, it's not the same quantity, but I just want to draw them together. Yes. So Simon Laughlin hypothesized that this input-output relationship is somehow tuned to this distribution in order to maximize the information that this sensory neuron is representing about X. So the idea is that this neuron has some constraints. It cannot generate an output which is smaller than 0. It cannot generate an output which is larger than R max. It has to work with these constraints. So it has to match the infinite range of X into this finite output range. And the question is how to do it in the best way. So we will use differential entropy of R as a way to quantify this and maximize it. But so we don't have time to do the exercise now, but I want to point out that what I'm drawing here kind of makes sense. If you're here or here, R does not provide much information about X because it saturates, right? But we don't care because these values of X are very rare. So the idea is that you want to be sensitive to X in those ranges where X has a reasonable probability to appear. And the more you can note that in the way I drew this curve, I should have drawn it like this. R is the most sensitive to X for the value of X that is most likely. This is the intuition behind why this looks like this, but we will do it precisely mathematically on Tuesday. Okay. כן, כי האינטגרל של T של X בעצם מ-0 עד L צריך להיות 1. אז אם מעבר ל-L ומתחת ל-0 זה 0 בהגדרה, אמרנו ש-T של X הוא קבוע רק בתחום הזה, והאינטגרל צריך להיות 1, אז הערך הקבוע שנותן אינטגרל 1 על האינטרבל הזה זה 1 חלקי L. אינטגרל של 1 חלקי L dx מ-0 עד L זה 1. נכון? אם הייתי שם פה קבוע אחר, זה לא היה יוצא.
נראה לי שמה שטלי היה אומר זה שאתה לא רוצה למקסם את האנטרופיה ב-R, אלא את ה-mutual information.
אתה מקדים את מה שאנחנו נדבר עליו ביום שלישי. אני רציתי להוביל למסקנה הזאת, שבעצם, כפי שאני הגדרתי את זה, זה לא הגדרה נכון.
יש לי כמה. כאילו, דבר הגיוני נראה לי שליצור פונקציה שאם אני עוזרת אותו, זה נראה בדיוק ככה.
מצוין, בדיוק מה שאתה.
סבבה? ויש לי שאלות לדבר שקודם. זה הגרף של האנטרופיה. כמו היה אני מסתכלת את השיעור, זה משהו, זה לא נראה ככה. זה נראה ככה?
כן, זה לא נראה, נכון, זה לא נראה, אבל זה כן הולך ל-0, זה כן 0.
X לוג X ועוד 1 מינוס X.
לא, זה פשוט, את צודקת, כל מה שהתכוונתי לומר זה שזה 0 פה ושזה 0 פה.
כן, אבל גם יש כאילו אמרת משהו על זה שזה מול C ב-0.5, זה לא יוצא ככה.
אז איפה זה יוצא?
זה יוצא
אוקיי,
לא מעניין. אבל כאילו אמרו, מה שכן הגיוני זה שאם אתה רושם פה את האנטרופיה של X, שעבור התפלגות בינומית,
כן, נכון. אבל לא, אני התכוונתי כן לגודל הזה, פשוט הייתי מגרושה על זה. אני יכולה לתקן ולצייר את זה יותר נכון.
לא מצאתי.
לא. וגם אני רוצה להוסיף הוכחה של הפכת עם אופסה לגרנג' אבל רק חשוב שזה אקסטרה מוביל אופס שזה מינימום. אז רציתי לשאול אם זה מספיק, כאילו דרך נכונה עכשיו זה פשוט להציב עוד נקודה ולראות שהאנטרופיה יותר קטנה.
כן, הדבר
כי בגלל שמזה לא מכל כיפה אחת.
זה לא מספיק בעצם, כי בעצם מה אנחנו עשינו? אנחנו נתנו פונקציה של הרבה משתנים שזה P בכל נקודה. ואנחנו רוצים להראות שכל פרטורבציה שתעשה, זאת אומרת, יכול להיות שזה מינימום גלובלי ושזה מקסימום גלובלי, ואז מה שהצעת, הדרך להבדיל בין שני הדברים האלה, אבל אולי יש שינויים מסוימים שבהם זה יגדל ושינויים אחרים שבהם זה יקטן, אולי זה מנותק. פשוט צריך לחשב את הנגזרת לפי כל אחד קומבינציות, אז בעצם צריך לחשב את מה שנקרא ההסיאן או הנגזרת.
אבל זה נכון להסתכל על ההסיאן כשאני מסתכלת על הגרנג' כאילו אני יכולה לדמיין את ה...
כן, זאת שאלה טובה.
או שאין פתרון פשוט. נטע אמרה משהו על הקביעות של האנטרופיה ולעשות את הגרנג' שלנו תוכל.
אני גם צריך רגע לחשוב על זה, מה קורה אם בודקים כשיש שופע לגרנג' אם זה באמת מקסימום. אני חושב שעדיין אני צריך לחשוב על זה. זה לא טריוויאלי, כי השופע לגרנג' הוא לא חלק מהפונקציה שאנחנו רוצים בעצם.
אפשר אולי את הסיאן של המסיאן, של הסיאן או משהו כזה.
אני צריך טיפה לחשוב על זה ואני נראה.
ראיתי את זה, כאילו בהתחלה תרגיל, לא הבנתי מה הדבר האחרון שאתה חושב בקשר
את יכולה להזכיר לי מה כתבתי? עם ה-conditional?
כן.
כן, אז אני אמרתי להם את זה תכונה ולא הוכחתי, שאם יש קומבינציה של סימבולים שאחד לבן שבאים מאיזו התפלגות משותפת, אז F של הקומבינציה אפשר לכתוב אותו בתור...
קורא להם זה S או H?
H כשזה בביטים ו-S כשזה בסכולן.
אוקיי.
ניטים אני קורא.
אוקיי.
פשוט כי לנו הרבה יותר נוח לגזור, אז זה בסדר גם תעבדי עם H, אבל רק אם זה בסיס 2. אז אני קורא, אז את זה אפשר לכתוב בתור האנטרופיה של X, כלומר לקחת את המרג'ינל של, רק לחשב את ההתפלגות של P של X, ועוד לכתוב את האנטרופיה של ה-conditional, y given X, ולמצע את זה על X.
שיראו את זה?
שזה כאילו האינטרפרטציה, שזה מספר הביטים שצריך כדי לקודד את ה-X, ואחרי שאת כבר יודעת את X, זה מספר הביטים שצריך בשביל לקודד את Y, שאת כבר יודעת את X. וזה צריך למצע על כל ההתפלגות של X. אז להוכיח את זה, מתמטית.
שיוכיחו?
כן. אני חושב שאני כמעט בטוח שנתנו את זה כתרגיל באיזושהי שנה.
לא נראה לי. לא רציתי קורא, רגע מחר. של X given Y נעשה X, נכון?
אני רוצה שהם פשוט יבינו מה מתמטית כל אחד מהביטויים האלה אומר.
זה לא פשוט קראת לזה כסמך אחד. אני קוראת לזה.
צריך להסביר.
השאלה שאני יודעת זה שאתה כותב כאילו .com, כאילו מה...
אני לפעמים עושה את זה כשזה איזשהו פרמטר. זה כאילו...
מה זה שונה כאילו משתם כאילו כמה?
אני מדגיש בזה את העובדה שהאנטרופיה היא כאילו פונקציה של המשתנה, של ההתפלגות של המשתנה. דלטה X אני חושב על זה פרמטר. אז לכן אני כותב נקודה פסיק, אבל זה לא...
שהוא...
פרמטר של ה-Differential Entropy.
אני חושב לא להיות ככה בשלב הזה.
בסדר, לא יודע, זה...
לא, אני פשוט ממש
כאילו, אחת מהצפות יש איזושהי טריינים,
אין לזה יותר מדי משמעות. כשיש איזשהם פרמטרים שהם כאילו לא חלק מההגדרה הבסיסית של האנטרופיה. כשפתחנו אנטרופיית שאנון, אנטרופיית שאנון היא מוגדרת כאנטרופיית שאנון שהוא משתנה אקראי, זה תלוי ב-X. עכשיו יש פה פרמטר דלתה X של הדיסקרטיזציה. אין לזה איזה... תחשוב על זה כמו פסיקים אתה רוצה.
שנייה.
לא,
כאילו קודם שאלנו, אין זמנים.
זה פונקציה גם של זה וגם של
כמה
זה.
ביטים צריך לחודד את זה.
כאילו מתאר בזה את העובדה שזה
מראה שככל שנשתמש בדמות נמוכה יותר, כדאי לקודד אותו יותר ביטים. ככל שלעצם יש הסתברות גבוהה יותר, כדאי לקודד אותו יותר ביטים. לא, רציתי להתייעץ אותך, אז אני יכול להתחיל מההתחלה פשוט. לא יודע אם זה ספרת הפרט מחקר שלי.
צריך להזכיר לי, אני לא זוכר.
כן, אבל הנתונים בהיררכיה פרדיכטיבית. אני מרשה כרגע במושג הזה להיות מעורפל, כמו שאלי ציין שהוא מעורפל.